Welcome. We are in Unit 6 on quadratic functions, and today we cover Day 2, quadratic functions. We are in 4.3 of the book, and we will cover 4 objectives. Graph a quadratic function using transformations, identify the vertex and axis of symmetry of a parabola, graph a quadratic function using its vertex, axis, and intercepts, and then find a quadratic function given its vertex and one other point. Let's get to it. So the first thing is graphing using transformations. Let's graph a quadratic function using transformations. First of all, what is a quadratic function? A quadratic function is a function that can be put into the form f of x equals ax squared plus bx plus c for some real numbers a, b, c where a is not actually 0. Here are some examples. You can see in each case there's an x squared in there, and we have those coefficients, and all the coefficients are real numbers. This last one, p of x, it isn't exactly in the form ax squared plus bx plus c, but I can put it into that form. So if I use FOIL and expand out that x minus 3 squared, I'll eventually get it into the right form. Since I can put it into that form, this is a quadratic function. If you graph quadratic functions, they look like parabolas, these nice arcs with a single turn in them. Now, parabolas can either open up or open down. When they open down, like the ones on the bottom two, those are called concave down. And if they open up, those parabolas are called concave up. So let's see how we graph a quadratic function using transformations. We'll start with the most basic, most fundamental quadratic function of all, y equals x squared, or f of x equals x squared, the most basic parabola. It has its vertex at the origin and arcs up nice and smoothly. What will happen if I transform this by pushing it up 1? If I move it up 1, look what happens. I add 1 to the function. Now this is x squared plus 2. So transforming vertically adds a little bit to the end of the function. Or if I subtract, by moving it down, I end up subtracting numbers from the function. Now, if I move to the right, look what happens. Something curious. Instead of adding, I actually subtract. And I'm not subtracting from the whole function, I'm subtracting just from the x itself. And so the x minus 3 appears, and that whole quantity gets squared. It seems a little strange that I should subtract, right? But let's just make sure that this is okay. If I plug in a 3 into the function, I expect to get 0 out as my answer. And yes, if x is 3, then 3 minus 3 is 0, and I get 0. And if x is 4, and I plug it in, I should expect to get 1 out. And that happens. If x is 4, then 4 minus 3 is 1. 1 squared is 1. So it works out okay. If I move it to the left, we end up actually adding numbers on the inside. And of course I can combine these. So let's say I move it up 3 units, and then I move it to the right 2 units. We have the combination. So the minus 2 on the inside tells me I've moved it 2 to the right. The plus 3 on the outside tells me I've moved it up 3. Or if I drag this down. So if you didn't have the picture, if you only had the function x minus 2 squared minus 1, you'd know it was shifted to, it was your basic x squared function shifted to the right by 2 and down by 1. Now let me do another demonstration. I'll take it back to the origin. I can flip this upside down, just like that. And now this is negative x squared. And if I do those transformations, the same idea happens. If I push it up, I'm just adding a little bit to each of those. And if I push it to the right, I subtract from the x itself. You see that? Okay. Let's play around with making this parabola skinny or wide. So if I move this point up, the parabola becomes skinnier and skinnier, And look what's happening. There's a number, a coefficient in front of the x squared that becomes bigger. So if there's a big number in front of x squared, it is a skinny parabola. But let me take that back down to 1. If I move it across, it becomes a very wide parabola. And look, the number in front of the x squared is very small, 1/64. But then I can also make these negatives. There we go. And now I have a negative in front of the x squared, negative and skinny. So it's a very big number, but big in a negative sense. Or I can make a very wide parabola. That's a negative coefficient in front, but it's very small. And then finally, all of these can be transferred up and down, left and right. So again, if you didn't see the picture, but you were just presented with this formula, you would know that the vertex was shifted to the right by 3 and up by 3. And then, since it's negative, you would know that the parabola opens downward, that it is concave down. And this 1/18th, which is a very small number, that would tell you that it's a very wide parabola. Okay, let's return to the slides. The vertex form of a quadratic function. Take a look at this. F of x equals 2, x minus 4 squared plus 7. This is a quadratic function in vertex form. This looks like those transformations we were just looking at. If you graphed it, where would the vertex be? Can you see? Well, this minus 4 on the inside tells me I've shifted it to the right by 4, and the plus 7 there means I've shifted it 7 up. So the vertex of this parabola is at 4, 7. Now, in general, the vertex form of a quadratic function is a times x minus h, some number, squared plus k, some number there. And it's the h and the k that tell me how the parabola has been transformed, how it's been shifted, and that hk is the vertex of the parabola. A, that guy out in front, that's going to tell us how the parabola opens, whether it opens up, whether it opens down, whether it's wide or whether it's skinny. So let's take a look at this. Describe f of x equals 2 times x minus 4 squared plus 7. Okay, so like we said before, the vertex has to be at 4, 7. And since the 2 is positive, this opens up. And in fact, I might even say, since 2 is bigger than 1, it's kind of a skinny parabola. So try these, pause the video, see if you can fill in the information here. Where is the vertex and how does it open? And then when you are ready to check your work, you can start the video again. All right, here are the solutions. So please check your work and we will move on. Okay, the vertex and the axis of symmetry. Here's a function given to us in vertex form, 2 times x minus 4 squared plus 3, and I can read off of this that the vertex must be at the location 4, 3, and that's what's being graphed here. But I've also graphed a dashed red line. That dashed red line is called the axis of symmetry, and the equation for that line is just simply x equals 4, the x value of the vertex. So the parabola with vertex hk has axis of symmetry x equals h. Whatever that x value is on your vertex, the equation of the line x equals 4, that gives you the equation for the axis of symmetry. So here is the big problem that we're going to face. How to find the vertex if the quadratic function is not given in vertex form. If the function is in vertex form, it is so easy to figure out the vertex. But if the function is not in vertex form, we have a little bit of work to do. So here it is. F of x equals 2x squared minus 6x plus 1. Where is the vertex? How do we figure that out? Well, here's the answer. We first figure out the axis of symmetry, which is x equals negative b over 2a. And then we can figure out the vertex by taking that x value and plugging it into the function. Here, I'll do a quick example. So let's take this. The a is the 2. The b is that negative 6. I carry the negative sign with it. And c is 1. And so the axis of symmetry is x equals negative b over 2a. Negative b over 2a in this situation is a negative 6 all over 2 times 2. And negative times a negative is a positive, so then I get 6 over 4, which is 3 halves. Then that's my x value for the vertex. How do I figure out the y value for the vertex? I just plug in 3 halves into the function. And so I get, and I'll spare you the details, that turns out to be negative 7 halves. So the vertex of this particular parabola is 3 halves, negative 7 halves. And the axis of symmetry is x equals 3 halves. Okay, why is this true? Let me take a second and figure out why should the axis of symmetry be x equals negative b over 2a. Here's the claim. If f of x equals a x squared plus bx plus c, then the axis of symmetry is x equals negative b over 2a. So let's graph this very generic quadratic function, f of x equals ax squared plus bx plus c. How would I figure out the x-intercepts? How would I figure out where it crosses the x-axis? And I do that by using the quadratic formula, perhaps, to find a solution, find those x that make ax squared plus bx plus c equal 0. So by the quadratic formula, those x values, those two x values there, are given by negative b plus or minus the square root of b squared minus 4ac all over 2a. But notice, those are really two different solutions. I have negative, if I split that into two fractions, I get negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. But look at that. So this smaller x value is really negative b over 2a minus stuff, and the x value on the right is negative b over 2a plus that same stuff. So where is this negative b over 2a? It is exactly in the middle. The axis of symmetry goes right through that number, and it goes right through our vertex. So there's our justification. The negative b over 2a comes from the quadratic formula. All right, let's try another example. Find the vertex for each quadratic function. All right, so negative b over 2a in this case is, well, you know what? It might be easier just to put my negative b on top, right? And then I can call that a positive 10 over, well, my a is 1, so 2 times 1, so that's 5. So 5 is the x value for my vertex, and then the y value is f of 5. F of 5 equals 25 minus 50 plus 27, and that equals 2. So my vertex is exactly at the point 5, 2. All right, here are two others. Pause the video, see if you can work these out. Where is the vertex? And then start the video again to check your work. All right. And we're back. Let's see what we have here. Negative b over 2a, so I have negative 12 over 4, which is negative 3. Then f of negative 3 is 18 minus 36 minus 5. That equals negative 23. So the vertex is at the point negative 3, negative 23. And for problem number 3, my negative b over 2a looks like 1 over 6, so 1/6. So my x value is 1/6. And then when I plug in 1/6 into the function, I get 3 times 1/36 minus 1/6 plus 1. Let's put that all over a common denominator. How about 3/36 minus 6/36 plus 36/36? And that gives me 33/36. And then I can reduce, divide the top and the bottom by 3. I get 11/12. So in fact, the vertex in this problem is 1/6 and 11/12. There we go. Graph with vertex, axis, and intercepts. So we're given a function, and if I can figure out the vertex and the axis of symmetry and some intercepts, that will help me graph it. So what is the vertex? Okay, first of all, like we've been doing already, let's figure out the vertex again. So negative b over 2a, I get 6 over 2, which equals 3. So the x value of my vertex is 3. Now let's plug in 3 to figure out the y value. So f of 3 looks like 9 minus 18 plus 8, and that equals -1. So the vertex is at the point 3, -1. 3, -1. What is the equation for the axis of symmetry? X equals 3. And how about the x-intercepts? Well, I want to take that function, x squared minus 6x plus 8, and set it equal to 0. Where it's equal to 0, those are the x values I want. So we can solve this actually by factoring. I think so, right? X minus 2, x minus 4. So it looks like x equals 2 or x equals 4. Those are the two x values that are the x-intercepts. So here we go. I'll graph those, 2 and 4. And now I can make a rough sketch of this parabola. Something like that. Now, if you wanted to, you could also figure out the y-intercept. Y-intercept. And to do that, you simply figure out f of 0. Where does it cross the y-axis? In our case, f of 0 equals 8, which is off the graph a little bit, but you can kind of see if this line kept moving up and to the left, maybe it would cross the x-axis, it would cross the y-axis right around 8. All right, here's another one for you to try. Do your best work and start the video again to check your work. All right, let's give this a try. So for the y-intercept, I can put a dot right at -5. Oh, and you know what? I have this axis of symmetry I haven't really used. Since I know there's a dot at 0, -5, there must be a dot on the other side of that axis of symmetry as well. All right, and so this gives me actually quite a few points that I can draw a decent graph. All right, so looking at some basic information, finding the vertex, and looking at the x-intercepts, I can get, and the y-intercept, I can get a nice rough sketch of this graph. Find a quadratic function given the vertex and another point. What is the equation for the quadratic function with vertex 2, 4 that passes through 5, 1? So we're really going in the opposite direction here. There's the graph. Now I have to come up with the function. We start by considering the vertex form of the quadratic function because I know the vertex. And so for the vertex form, I can just plug right in that h is 2 and that k is 4. So for this particular parabola, f of x equals a, x minus 2 plus 4. And now it remains to figure out what is the a. How do I do that? Well, I need to use the fact that it passes through 5, 1. What that means is f of 5 equals 1. That's what it means for the point 5, 1 to lie on the graph. F of 5 equals 1. Well, let's take my f of x and just plug in 5. I'm replacing that x with 5. And so I get a times 5 minus 2 squared plus 4 equals 1. Now I can simplify the left. 5 minus 2 is 3. 3 squared is 9. So I get 9a. I subtract 4 from both sides. I get -3. 9a equals -3. Divide both sides by 9. a equals negative 1/3. Now I can take that negative 1/3 and put it in place of the a. And that will complete my figuring out the f of x. So f of x is negative 1/3 x minus 2 squared plus 4. Or if you really wanted to, I'm not doing the details here, you can expand this all out and get your quadratic function in sort of standard form. You try. What is the equation for the quadratic function with vertex negative 3, negative 3 that passes through the point negative 2, 1? Take a few minutes, give this your best try, and then start the video again when you want to check your work. Go to it. Let's take a look. So we start with the vertex form of the function, plug in negative 3, negative 3. Be very careful, watch this. Since my x is negative 3, I'm actually adding 3 on the inside of the parentheses. F of negative 2 is 1. I use the fact that it goes through that additional point. What is f of negative 2 really? I just replace the x with negative 2 up above, do some simplifying, and I can figure out what a is. It turns out that in this case, a is 4. So I plug in 4 for a, and I find f of x equals 4 times x plus 3 squared minus 3. Or you can expand it all out and get your function in standard form. All right, so we've done a lot with quadratic functions. We've taken a quadratic function and we've looked at it as a graph. We've taken graphs and found out the quadratic functions, examining these parabolas and thinking about transformations. Lots and lots of good stuff. So this is a good place to stop, and I will see you in class.